All right. Well, thank you so much for that wonderful introduction. And it's lovely to be back here in London, Ontario. This is a bit of a homecoming for me. I did my postdoctoral work here about 12 years ago, and it's really, really wonderful to have the opportunity to come back and to have a chat like this with all of you tonight. So what I'm hoping to do is to talk a little bit about the dialogue that's happening between two different disciplines. We've got planetary exploration, where we go out and use spacecraft to explore the worlds in our own solar system and to learn new things about our family of planets, close to our parent star. And then there's exoplanetary astronomy. That is a discipline where we're using telescopes to look for new planets around distant stars and to really understand what's going on with those. But both of these types of planets, they both share the same kinds of processes. They both work in the same ways. So we can potentially translate between the two of them using a Rosetta Stone of sorts. And I'll get into that in just a couple of minutes. I know we had a little bit of a discussion about Gerhard Herzberg, but I wanted to throw up a slide as well here. Whenever I'm giving one of these lectures which has a particular name, it's nice to take a look and see what that person wrote, who that person was. And something that I thought was really interesting about Professor Herzberg is, his emphasis throughout his career on humanity, humility, and humor. And of course, he did this within a lovely, lovely sort of background of strong social networks, strong family ties, strong collegial ties. So what I've tried to do in this lecture is to include elements of each one of these. So for the humanities side, I've reached out to colleagues of mine. I've gone and asked them for suggestions of what I should include, and some of them have contributed slides, and you'll see that. For humor, well, I'll have to leave that up to you as to whether or not I'm funny, but we'll see. Humility is always necessary in a scientist. That's a very important property. And I've got to tell you, we're going to need a little bit of humility as we start this, because we are going to start with the weird ones. Here are some really, really strange exoplanets that are out there. And some of them are a bit of a mouthful. So let's, for instance, take the one over here on the left. So that's KIC 125575448. Pause for breath. This is a rocky planet very close to its parent star. It's maybe about the size of Mercury, but it's so close that it's being torn apart, and it gets this sort of comet-like tail going on here. It's a disintegrating Mercury, we call it. The next one over here, WASP 193b, this is a fairly recent discovery. This one here is a planet that is so not dense that it's actually lighter than cotton candy. And of course, we have some generative AI here giving us an idea of what a big ball of cotton candy would look like. And then we've got this one over here, one of my favorites, WASP 76b. This is a place where it's so hot that you get clouds, but the clouds, instead of being made of water, are made of molten rock. And you get this sort of rocky crystal rain that just comes down on the division of the planet between the day and the night side. They're really, really, really strange places, I have to tell you. So how do we actually, go about understanding such strange worlds? How can we figure out these types of processes? Well, the best way that we have to do that is to actually compare them to the planets in our own solar system. Those are the ones that we know the best, and they give us the best possible means, the best possible attempt that we can have to actually translate between these different planets. And it turns out that we can take a look at those planets to gain some understanding. And everyone in the room, you already know a little bit about this, and I'm going to show you why in just a second here. So let's take a look at this image here. We've found something like 5,600 exoplanets now. They're not all up here. I don't have a screen big enough to show that, but we've got a lovely collection up here. And I can imagine that everybody in the room taking a look at this picture saw planets, not pieces of fruit, not various balls used in various sports or anything like that. These are very, very planety. And there is a reason that they look that way. Let's take some very specific ones. Here's two I want to compare directly. On the left there, we've got a planet that should be familiar to most of you. On the right, we've got an exoplanet, Kepler-62e. And what we notice about these is we've got oceans, we've got continents, we've got clouds. Absolutely wonderful. Earth is an image taken from space. So this is us looking back at our little blue garden planet. The other image, Kepler-62e, is that a telescopic image? Is that something that we have captured in our exoplanetary astronomy? Well, it turns out that it isn't. It's an artist's impression of what that planet looks like. But it's probably not wrong. That's the really crazy part. Artists, when they're creating a canvas, when they're creating something, they tend to use references. They look at examples as they create whatever work they're working on. And so what the artist has done, and sadly, this is not Bob Ross that has painted Kepler-62e, but what they've done is they've looked for examples of similar places in our own solar system and happening upon the Earth, and thinking that similar processes must be occurring on Kepler-62e, you get this lovely picture. So the continents are probably not in the right place, neither are the clouds. We don't know how much ocean there is, but this is probably not a bad representation of this place. And it's something that really appeals to our human senses. Let me show you the best real images that we have of exoplanets. So here's a system. This is HR 8799. And this is the best snapshot, I think, that we have, pretty much, of an exoplanetary system. So you've got a star in the middle. Its light is being hidden by a trick of the telescope. We work really hard to tamp down that brightness, because looking at planets around other stars is like trying to find fireflies that are, next to a spotlight. It's really, really difficult to do. And you can see this particular system, there are 4 different planets. And we astronomers are very creative people. So they are B, C, D, and E. It's an interesting system. You can actually follow this system over time. You can watch those planets go around the star over here over the course of several years. And it's a fascinating place, but it's not a typical place. It's not like our solar system. The distance between the Earth and the sun is something that we call an astronomical unit. We use that as a shorthand. And our whole solar system fits within about 30 astronomical units. That's how far it is to get to the furthest planet, which is Neptune. Sorry, Pluto fans in the room, there will be some slides for you later. These solar systems are much bigger. So we've got a little scale bar down here, which is 20 astronomical units. So planet E, the closest one in, is about that far. But planet B is much further away, well over 100 astronomical units. This is a much bigger solar system than our solar system. The reason that we can see it is because those planets are further away from the spotlight, so it's easier to make them out. And this system is also very young. That means that the planets are all puffed up and they're very hot, which also makes them much easier to see than planets around stars like our own. So you might ask with something like this, we've got these images here. When we want to go out and see planets in our own solar system, we send a spacecraft. Why don't we just do that? Let's send a spacecraft. Let's get that picture like we had of Kepler-62e. Let's bring that home and put it in the New York Times. Well, there's a real practical reason why we can't do that. And that's that the stars are simply too far away. If you were to take the closest star, Proxima Centauri, and it does have a planet, by the way, if you were to go there using the fastest chemical propulsion rockets that we have, traveling at a speed like Voyager 1 has, it would take you 70,000 years to get there. And I don't know about you, but I'm a very impatient scientist, and that's too long for me. So there are other fellow scientists who are trying to figure out ways of doing it. And we've got this idea up here. This is Project Starshot, they call it. The idea here is to create a teeny tiny spacecraft, maybe only the size of a little chip, like in a cell phone, and to put it on a great big solar sail made out of the same kind of material as in a chip bag. And then to have a Dr. Evil class laser there ready to send it out to the stars at a good fraction of the speed of light. Even that takes decades to do. So sadly, in our lifetime, it's probably unlikely that we're going to have images that are as good of exoplanetary targets as we have in our solar system. So you might be tempted to ask, why bother? Can we actually know these places as real worlds, or will they be forever, bumps and squiggles on a graph or points of light in the sky? And the truth is that we can, but we need to listen carefully to the language that's being told to us by their parent stars. That's what gives us the words and the sentences and all of that we need to put into our Rosetta Stone. Let me show you a little bit about that process. So if we've got a star that has planets, what's going to happen? We can't see those planets most of the time directly, especially not if they're like the planets in our solar system. But what we'll notice, if the system is oriented just right, that it'll be a bright star that will suddenly dim just a little bit every so often. And this brightness and then dimming, and then brightness and dimming, this repeats over time. We get this nice regular pattern that happens. Astronomers call this the transit method of detecting planets. And the reason we call it the transit method is that we have a strong, strong suspicion for what's causing that dimming. It's the planet, it's the shadow of the planet passing in front of the star. That makes the star look dimmer to us. And as a result, the amount by which that star gets dimmer tells us something about how large that planet is. So you can see in the animation up there, we've got a terrestrial Earth-like planet, and we've got a Jovian Jupiter-like planet passing in front of the star, and they cause different amounts of dimming. We've actually gotten to be really, really good at detecting that dimming. If I were to take the example of an object that's pretty bright, like say First Canadian Place, which is a skyscraper in downtown Toronto, if you were to turn on all the lights in every office on one side of this building, our ability to discern differences in brightness would allow me to go into one office in this building and to go to the lamp, to the window shade, and pull it down by 1 centimeter. And we could see that difference when we're looking at stars light years away. So that lets us detect these really small, comparatively, planets around these really, really distant targets. It's really wonderful. It's amazing. And when you combine that information with other information that we get about planets, so not just from the transit method, but we have other methods of exploring the parent stars and how their planets affect them, we can get different size shadows that tell us about what these planets are made of. So if we imagine that we have a planet that's 1 times the Earth, same mass as the Earth, or a planet that's 5 times the mass of the Earth, and we imagine making it out of different stuff, from iron all the way to hydrogen, you actually generate all these different shadows. So by comparing the shadow with the mass, you're actually able to figure out what kind of a world it is you're looking at. Is it a Jupiter-like planet? Is it an Earth-like planet? Is it something like Mercury? Or something even weirder? We can get more information than this too. We're only thinking about one color here. We're thinking about that shadow just in one color. If we go and we get a whole bunch of different colors, if we take after Herzberg and we do some spectroscopy, well, then we can get even more. So it turns out that because we've got this really, really good ability to discern brightness, what we can do is we can detect not only the shadow of the planet, but we can detect the light that passes through that planet's atmosphere, around the edge of the planet as it goes in front of its star. Different compounds in the atmosphere of the planet can block light to greater or lesser extents. So if you have something that blocks light really effectively, the planet actually looks bigger at that wavelength, at that color. And if the atmosphere is transparent, then that light comes through and the whole planet looks to be a little bit smaller. So because this happens at different colors, we're able to actually figure out from light years away what compounds are in the atmosphere of a planet like this. That's just really fascinating and blows my mind, I can tell you. So we have these different bits of information that we're getting from the stars. We get all of these different ideas. And I've shown you the best cases. I've shown you the pretty ones, the ones where it's very straightforward. But most stars don't look like that. They have a more complicated, language that they're telling us. And so, how are we ever going to figure this out? How are we going to be able to do this? And the worst part is that it's actually even worse than that. Because we don't know much about these places. We've got these bumps and these wiggles on the curve, but not much more than that. So let's do a little thought experiment here. Let's imagine Mars as an exoplanet. So imagine we're in another solar system. We're looking back at our solar system, and we're watching Mars pass in front of the sun. So let's imagine that we know when Mars is going to pass in front of the sun, and we take pictures every 30 seconds as it's doing that. If we do that, then we're going to end up with about 8 megabytes of data. Not a lot, not a lot. And this is, a really, really good example. If we imagine then we're going to do every color we can think of, we're going to take the resolving power of the James Webb Space Telescope. Now we're up to 15 gigabytes of data that we can get out of this. So this tells you about the absolute best case of what we can do from another star. Let's look at the planetary side. Mars lives in our solar system. We have other ways of interrogating it. So we could imagine looking at Mars with a deep space observatory, like the Deep Space Climate Observatory, for instance. That gets us up to 39 gigabytes. And if you were to use something that's in low Mars orbit, for instance, like the Mars Reconnaissance Orbiter and the HiRISE camera, then you now are up to 19 exabytes. It's a crazy amount of data. It's obvious that we know Mars much better from in the solar system than we do from outside of the solar system, from anywhere else in the galaxy. And the amount of data here is just absolutely, mind-boggling, I have to tell you. I'm going to show you in a second a way of thinking about this. So just remember that for most exoplanets, we have less than this, sometimes just kilobytes of information. So I'd like to, show you a little bit of prop here. So all the data that we have for most exoplanets, it's on one of these things. So for those of you in the audience under 30, this historical artifact stores about 1.4 megabytes of information. So we can think about those numbers in the last slide in terms of how many floppy disks here that we need. So for the exoplanetary light curve, for just watching the shadow as it passes in front of the star, we need about 6 of these things. So that's about the width of a dime. Not very many. That's perfectly considerable. You had to put a lot more of these in to install Windows back in the day, let me tell you. If you are doing the exoplanet with spectroscopy, you need a blue whale size stack of these, about 10,000 of them, which is considerable. Let's come back into our own solar system. If we observe Mars with an observatory in orbit, an observatory in deep space, we need something more like the Peace Tower for the Parliament buildings to do that. And my personal favorite, if we have something like HiRISE, then what we need is a stack of floppy disks that starts at the surface of the Earth and that actually goes all the way to Mars in order to store all that data. Almost 50 million kilometers stack of floppy disks, which is probably more than all the floppy disks that have ever been manufactured. So thank goodness we don't use those anymore. Really, what we need, since we're never going to have that amount of data from these exoplanetary places, is we really need to think about that translation. How do we use what we know in our own solar system to tell us about these places? And that brings me back to the Rosetta Stone. I wanted to take a couple of slides and sort of formally introduce you to this artifact. So the Rosetta Stone was a real big find for people who studied ancient languages. By the time that it was found, the ancient Egyptian language had been lost. Nobody knew how to translate these strange pictograms here. and the collections, how did this language even work? So unfortunately, though we knew the ancient Egyptians had a language and that they wrote many things down and their buildings were, of course, covered with these sorts of things, we couldn't read them. So when this was found, the really wonderful thing about the Rosetta Stone is that it contains the same text, but written 3 different times. The top part of the stela here, of the stone, that's in hieroglyphics, in ancient Egyptian. The middle is in Demotic, and the bottom is in ancient Greek. And our friends over in archaeology said, aha, I can read ancient Greek. So you can use that then to go back and figure out what the hieroglyphics mean. And that proves to be extremely, extremely helpful to understand, all that was going on in ancient Egyptian culture. So can we do the same thing? Can we take all of those bumps and wiggles on the graph that we learned from listening to the language of the stars that have planets, and can we turn them then into actual planets? And we do that by analogy with our own solar system and what we learned about planetary processes from going out with spacecraft and asking the planets that are nearby. Well, we started to do that. Here is the best image that we had of the planets before we went out in a spacecraft. And so our very first test was to go to the closest planets and try to understand them. So of this family of planets here, we have Mars up here. And believe it or not, this is Venus down here. Venus is always closer to the sun than us, so we always see it as a crescent. Now with Mars, we saw an ice cap at the top. We saw, the color of the sort of reddish part change over the year. And based on our terrestrial experience, we said, aha, that must be vegetation that's changing. And that vegetation must be fed from somewhere. We don't see oceans. It must come from the pole. Venus was even better. Venus was completely white to us, covered in clouds. So we could imagine anything we wanted underneath those clouds. And we thought about places on the Earth that have a lot of clouds, like the tropics. And so you get images like these. So here on the left, we've got an image of a Martian canal, created by a dying civilization, funneling that water from the polar caps all the way to the equator. And then on the right, we have the dinosaur civilization here. This lovely, fantastical image by Frank R. Paul. You can see some interesting forms of transit up here and down there. A little bit unconventional, still probably faster than London Transit, frankly. But we now know that this picture is not correct. We've sent spacecraft out and we've seen different things. So on the bottom, no dinosaur civilization, sorry. Just basically the oven on self-clean cycle. We've got these platy rocks. We've got this really yellow atmosphere, and it's sulfuric acid clouds and all sorts of stuff. Not fun. Up here, we've got the Curiosity rover investigating Mars, and we see the sands and the dust that rule this planet now. But the fun thing about going to these places is we can actually ask deeper questions. We can ask what kind of places they used to be, not just what they are right now. And what we find is that in both of these places, we actually have good evidence that there were liquid oceans at one time. So both of these places were a lot more clement, more like our imaginations than they are today. All right, we didn't do so great with Mars and Venus. We learned our lesson. Let's try going a little bit further. So here is the discovery of the planet Pluto. I told you Pluto would be back. Here are the initial discovery plates from Clyde Tombaugh in 1930. And the way at that time you discovered a new planet is you took pictures of the sky and you looked for the dot that moved. So everything else in this plate stays in exactly the same place, but Pluto moves. And from that, we were able to tell that it had to be in the solar system because all of the other points of light are fixed stars in here. And we know roughly, because we know how fast it moved, we knew it was in the solar system. We knew how far away it was. And because of how bright it was, we knew roughly how big it was. So we had a good start here. And we kept observing Pluto over time. And our view of it got a little bit better. and a little bit better. So here on the left, we just have that one dot in the image blown up. By 1994, we were able to tell that it was brighter in the middle and dimmer on the edge, which normally means that there's some atmosphere going on. So we learn more information. And then in 2003, we were able to use some sophisticated analysis to get a bit of a pattern of bright and dark. For the best exoplanets, this is kind of where we are right now, that 2003 image. But when we sent a spacecraft out to Pluto, we wanted to do better. We needed to know what kind of a place were we expecting in order to decide what kinds of instruments to send, how would we arrange them, how are we going to actually manage this encounter? So we needed an example. We needed something to which we could compare Pluto to give us an idea. And it turns out this is a good example here. This is Triton. Triton is the largest moon of Neptune. It looks like it's been captured from further out in the solar system for Triton. And that's because it orbits in a retrograde way, which is very strange. So we were thinking that this is probably what Pluto looks like. And we saw this sort of yellowish, reddish kind of terrain out here. We also noticed a lot of black streaks. You can sort of see them all trending in the same direction here. That's from geysers coming out of the solid nitrogen here, and then being carried away by the winds. So we said, aha, Pluto, we don't know what it's going to look like exactly, but it's probably something like this. So in advance of New Horizons making it out to Pluto, we got this artist's image. And here we have that sort of orangey reddish terrain. We even have one of the geysers there. Here you can see Charon, which is the biggest moon of Pluto, and you're a long way from the sun. A little bit of atmosphere from that Hubble telescope image. So let's see, how did the artist do in this one? Not too bad. Same kind of color on it, so the same kind of materials. Looks pretty good. Maybe a little more reddish in some places, a little bit more yellowish in others, but that's not atypical. And oh my goodness, just check out this heart-shaped feature there. I mean, was there ever a bigger gift to public outreach talks? I mean, wow. What a success, what a success. So hooray, we're getting better at this, of actually using planets to understand processes that we can then apply to points of light in the sky. And the nice thing about this is that every time we do it, we get a little bit better. Pluto wasn't an exact copy of Triton. It's a little bit different. And the thing that was the most different is the atmosphere. Here's an image looking back at Pluto after we'd gone by. And you can see all sorts of interesting features here, but I'll show you, I'll just let this come up again. You can see all of that scattering from the atmosphere, all that bright light. It's like dust on a windshield. And that's a whole lot of material, this sort of dusty, tholin-y stuff, we call it, that's sitting up there very calmly. When you go and you pull back and you take a look at the entire atmosphere, you find that Pluto's atmosphere is actually much more puffed up than even the Earth's is. And that was not expected. Instead of things like geysers, we got a whole bunch of different surface geology going on Pluto. It's a fascinating, fascinating place. So we've got places that are sculpted by the sun. This is sometimes referred to as snakeskin terrain. And those ridges are 500 meters tall, maybe a couple kilometers in between. You can see the same kind of texture, by the way, in a snowbank as it melts in the spring. So keep an eye out for that next March. Down here, we see sand dunes arrayed in lines. This is actually little pieces of water ice that behave like concrete at these temperatures. And they line up to form this interesting sort of beachy kind of plain. And then over here, we have this little cauldron of nitrogen ice sort of bubbling on very slow time scales. So all sorts of really interesting, fascinating things happening there. No geysers though. And so afterwards, after we visited, we actually went back and we commissioned the artists to create a new image. And you'll notice that this one looks a lot more like the Pluto that we found. So we get better at this over time. So, all right, we've learned about planetary processes within our own solar system. Let's go and apply those out in the exoplanetary realm. And let's try a really hard problem this time. Let's take a look at what makes a planet habitable, because really, when we're looking at planets in other solar systems, we're very interested to see places that might have signs of life. So what do we need to make a planet habitable? Based on what we've seen here in our own solar system? Well, the first thing you need is some liquid water. That tends to help. By the way, this is how I dress anytime I'm going into Lake Ontario. So don't think this is strange. You need to have liquid water because liquid water gives you a place where you can actually go ahead and have all of the chemical reactions you need for life to occur. They need to happen in a place. It doesn't happen very well in a gas or in the emptiness of space. On a surface is okay, but a three-dimensional volume, and water is perfect for handling these kinds of compounds. It's a wonderful, wonderful medium. So liquid water, that seems to be important. Can that liquid water be anywhere? Well, if we think about places like this is Enceladus, which is a moon of Saturn's. We have a really exciting thing going on here in that there's water, liquid, inside this object, inside this moon. We know it's there because we can see it jetting out into space. You can see those little things down here. That is really, really exciting. I would love to see a place like Enceladus explored, to get in under that ice, to see what might be there, because it could be anything, maybe even this, you know? It would just be amazing to get down there and to see if in that liquid water, is it not just habitable, but is it inhabited? There's also fundamental reasons for wanting to go to a place like this. On the Earth, we know that there's this question of whether life originated in pools on the surface or whether it originated deep in the oceans around deep sea smokers. And with a place like Enceladus, only one of those theories can be true. So if it's inhabited, it really tells us something about our own origins. That said, for the purposes of wanting to interrogate exoplanets, Enceladus is kind of useless. Even in our own solar system, we don't know if anything's living in Enceladus. And if we were to think about these places in other solar systems, there is no way for us, unfortunately, to interrogate this from afar. So unfortunately, we do need to leave behind the icy moons, even though they have more livable volume than all of the Earth's oceans combined. It's a wonderful topic of exploration, but it doesn't help us here. Instead, what we need is atmospheres. Atmospheres are key. Remember that we can look at the light that comes through those atmospheres when those atmospheres pass in front of stars. And so we can look for compounds like water in the atmosphere that tell us about what's going on the surface. And we have found places where there is water. For instance, here's a spectrum. So this is just the different colors of light from 0.3 out to 5 microns. And there are features in here where we see distinctive absorptions due to water. So there's some here and here, here. So hooray, there's water in the spectrum and in the atmosphere of WASP-39b. Only problem is WASP-39b is what we call a hot Saturn. So it's also 800 degrees centigrade. So the liquid water thing we kind of lose out on a little bit, but it's a promising sign. And we've continued to make improved discoveries around places that are more and more clement. The heat is important. You also need a place that's not too hot and not too cold. And it's not just because you need your water to be liquid. So here I'm showing a couple places in the solar system. We've got Io up here, which is the most volcanically active body in the solar system. It's a moon of Jupiter's. And here's a couple of shots of the plains of Mars, where you can see, a little bit of snowfall, making them look especially cold. Turns out you do need a little bit more detail on temperature. And it really matters because, again, we go back to the chemistry of life. As you get warmer, the reactions that you need to build up life happen faster and faster. Titan has all the right ingredients. That's the moon of Saturn's. Titan has all the right ingredients, but they move around too slowly in the dance. The temperature on Titan is 200 degrees below zero, that they never can really come together. At the same time, if you increase the temperature too much, then you wind up in the situation where the reactions that take life apart happen faster than the reactions that build life up. So you can test this. If you have a bonfire and you go and you walk into it, you'll probably find that you will burn faster than you will heat. So that's an example of an environment that's too hot for the chemistry of life. So this is why temperature matters. We can put that temperature limitation together with the liquid water limitation, and we can come up with a place that's just right, the Goldilocks zone, the habitable zone. So right in the center of this here, I've got our own solar system. So, we have our beautiful yellowish sun-like star, and you can see all of the planets. And this sort of teal colored region here, that's the habitable zone. Could be a little bit wider, could be a little bit narrower. We're still working on that as we interrogate our planets. But in theory, it is the zone in a solar system where if you have an atmosphere, you can have liquid water on the surface. Any kind of atmosphere we can imagine, would be the width of the habitable zone. And the atmosphere is important. The Earth, right smack dab middle of the habitable zone, best real estate in the solar system. Right next door, the moon, no atmosphere. I don't want to spend the weekend there. It's a little bit cold and a little bit hot at the same time. It's not a habitable place. So it's something we've got to keep in mind. We do know some basic rules, though. As you make your star bigger and hotter, the habitable zone should move out. You want to get further away from the campfire. And as you make your star smaller and less luminous, then the habitable zone moves in. And it gets a lot closer. And that's important because most stars in the galaxy are actually the smaller stars. Let me show you one of our favorite stellar systems. This is the TRAPPIST system. Oh my goodness, a lot of planets here. Just count them. 1, 2, 3, 4, 5, 6, 7 planets. And those are Earth-sized planets. Those are impressive rocky bodies. Not only that, but we've got 3 of them that live in the habitable zone, E, F, and G. That's exciting. Maybe we have some places where, we could have some life. This is a really tiny solar system. If I draw this and compare it to our own solar system, you'll notice that the whole thing actually fits down here well within the orbit of Mercury. So it's a very, very compact system. You can't help but look at a system like this and think a little bit about how it would look to actually stand on one of those planets and to consider the night sky. So I'm going to dim the lights here and let's take a look. So you have to imagine looking up at the night sky and seeing places larger than the moon, places where maybe you see continents, where you see clouds. In this interpretation here, maybe you even see other civilizations. Can you imagine, what goes through the minds of anything that might be living in a place like that? It's a fascinating, fascinating world. So, are these places inhabited? Jury's still out on that one. We've started looking with Webb for atmospheres. We haven't found them yet. It's not completely excluded from possibility, but these are looking less and less likely, unfortunately. Maybe they're not the best place for us to go and look for habitability. Maybe we need to look at something stranger. So this is another lovely exoplanet. This is TOI 715b, and this is a super Earth. What that means is it's the planet that is intermediate in size between the Earth and the smallest gas giants, Uranus and Neptune, somewhere there in the middle. By the way, this is the kind of planet that artists have a hard time dealing with because there's nothing like it in our solar system. I love this particular image here. I love the greens. I love the reds. But other artists look at this planet and they see something different. So also, same planet, different artist. This one looks a lot more like a gas giant. I like the next artist. The next artist really hedged by drawing nothing. Just the limb of the planet there. And this one's my favorite. Kind of half and half. Could you actually get a planet like that that's half and half? Probably not, but it's pretty. So at least we have that. Super Earths are interesting because given their size, they should have very thick atmospheres, but still solid surfaces. So anything that happens down on the surface of the planet is going to be more protected than it would be if we were just at Earth 2.0. Something like this doesn't exist in our solar system, but we can get at it from thinking about smaller objects and building up and bigger objects and building down. And because in our solar system, we have the ability to go out and ask deeper questions through our space exploration, what we can do is we can get at those kinds of processes to help us understand. We can look at meteorites that tell us about how these planets formed, what were the materials that they came from. And then we can look at how those materials assembled and evolved over time by visiting the planets themselves. So I think it's pretty, we've gotten good at taking the planets in our own solar system and projecting that out and thinking about planets in other solar systems, but they can also tell us a lot as well when we think about our own solar system. So we can learn lessons from the diversity of different planets that exist out there in the galaxy and the different things that we see. And just like knowing Greek, lets you perhaps know a little bit more about hieroglyphics. If you knew things about hieroglyphics, it could explain some of the assumptions that you made about Greek or any two languages. If anyone in the audience speaks more than one language, you'll know that there's a bit of a mindset difference between the two of them. Of course, we have French and English here in Canada, and I can tell you, speaking both languages, that there's just a different way of coming at the same concepts, and we can explore it in different directions. So one of the things that astronomy is really good at is telling us about the large scale sweep of things. We can look out into the cosmos and we can observe examples of really anything you want, any kind of solar system at any time in its life. And we're really good at finding out about birth and death when it comes to solar system. Our solar system is middle-aged. We're a long way from being born, we're a long way from dying. But we can look at what's out there and get a little bit of information on that. So here is the Orion Nebula. It's one of the brightest nebulae in the sky. I'm going to zoom in on this one. And let me identify some of the objects that are in this field here and blow them up a little more. So here's 6 of them. These are baby solar systems. They're brand new. Stars have just turned on. There are little disks of spinning gas and dust, and they're ionizing and brightening things in their immediate vicinity there. So these are solar systems being born. And so as a result of looking out at places like this, we understand better where our own solar system came from and what its origins were, what it looked like when it was very, very young. We can go to the other end of the spectrum as well. We can think of where we're going as a solar system. And it turns out you can, die with a whimper. That's an example here of the Ring Nebula on the left, where a star has, puffed out its outer layers, cooked its planets, and has become sort of a still glowing cinder in the middle. Or you can go out with a bang. This is the Crab Nebula. It looks like an explosion in this web image, doesn't it? This is a star that went supernova and just tore itself apart. So we know from looking out into the cosmos what the beginning and the end of our solar system look like. With time, we're going to get more gradations of that. We're going to be able to ask deeper questions and more subtle questions. A very interesting one for me is thinking about things like climate. How do we move from a garden planet like the Earth to a desolate wasteland like Venus? What are the tipping points in there as we increase our own planet's temperature? Is there a point where maybe, we push too far? And with enough examples in enough different solar systems, maybe we can start to get at what those points are. So I want to leave you with a final couple of thoughts. Within our solar system and without, there are still so many questions to be answered, so many interesting things to explore and to discover. And what I've got here is an image from the inside the atmosphere of Jupiter. So you can see this lovely picture. This isn't a real picture. This is an artist's rendering. And it's a rendering that was put together by Carl Sagan. And you can see, Carl's back here, back of his head and his turtleneck and all that good stuff. It's really, really amazing that we can go and we can, take a look at questions like this. And really how lucky we are to live in this time. It's the first moment in human history when we are actually going out and visiting other worlds. And the reason that Carl had this particular painting commissioned was he wanted to put things in it. And in particular, if you look closely at the painting, you'll see these three sets of things. So here we have at the very bottom, these are plankton-like organisms that he called sinkers, things that just get picked up on updrafts and then sprinkled down. He imagined that maybe those things were being eaten by giant bags of gas that he called floaters. And maybe the floaters were being hunted by things that he called hunters. Carl keeping, of course, with the creativity aspect here of naming things. Really, really fascinating. Could something like this exist in a place like Jupiter, a place in our own solar system, a place that we allegedly know well? Well, let me show you real pictures of Jupiter. So here we have some lovely swirling mixing between two different bands. So sort of like in these regions that you see between the different bands. And what I want you to pay attention to in this image is these little pinpricks, these little white pinpricks up here. Each one of those is a 50-kilometer tall thunderhead, like this one, but bigger. They look so small, they look so insignificant here, but they're massive convective formations. And that is one of the highest resolution images that we have of Jupiter. What's fascinating about a place like this is that the closest, the most high resolution images we've ever received of Jupiter are about 4 kilometers per pixel. So there's actually no way that I can tell you for sure that Carl's poorly named biosystem doesn't exist. And it's just fascinating to me that even in a place we know well, there are still questions of this magnitude waiting to be answered. And if we've got these kinds of questions here in our own solar system, imagine what waits for us in other solar systems. So I want to show you one more picture. And I'll just bring down the light so you can see it a bit better. So take a look at this place. We started out with those views of HR 877, and we were looking at individual exoplanets, just points of light, like this little blue dot up here that you could imagine just sort of sitting there in a sunbeam like this. What kind of stories does a place like this have to tell us? What could be going on a little dot like that? Well, this one actually you probably know pretty well. That's a picture of the Earth taken by the Voyager spacecraft when it was 6 billion kilometers from home. Looking back, this is the last image that it took. And when you think of a place like this is a place that contains, everybody that you know, everybody you've ever known, everybody who's ever lived, every story you've ever heard, any place you've ever been. In fact, all the known light that exists in the universe right now is sitting on that one pixel up there. And then to think that there are hundreds of billions more of these out there to be explored, to be understood. That's the sort of questions that I find fascinating as a scientist. And that's where I leave you for tonight.
Thank you, Dr. Moore. My gosh. Fascinating, interesting. And I realized how insignificant, I knew I was insignificant, but Perspective. Perspective is everything. uh, Question time. So, Dr. Moore will take questions, and I know you have burning questions. So just indicate if you have a question, and Bill will run up.
When doing these spectral analyses for exoplanets, is there a way to tell the temperature of the atmosphere or the, I don't know, like average temperature on the planet, or is there no way?
There are ways to do it. I mean, a lot of it focuses on, how much energy you have going in and, how far that planet is from the star. But you can take a bunch of different factors. You can make models of what the spectrum should look like based on what's in it and the different temperatures that it's at, right? Because you expect different species, you expect different widths, the amount of color that's being taken up by a particular compound. So people try to fit that. Often we don't have as many points as we would like. So, it's a challenging thing to do. But yes, yeah, temperature is something we look at in that way. And clouds are awful. Well, I personally like clouds, but they make spectra hard.
How limiting is the transit method? Because isn't it dependent on the orientation of the orbit with respect to us? So like, how many planets do you miss out on because of this?
Most of them, I would say, you have to have that really, really good alignment to see planets with the transit method. But what we can do is we can run statistical models of all the different orientations that we have. And in looking for, doing surveys of these things, we've gotten to the point now where we can guess with confidence how many systems there ought to be out there that we can't see because the orientation isn't quite right. And that's where the estimate that you have more planets in the galaxy than stars comes from. But yeah, you only see a few. It's true.
Thank you. I have two questions, a short one and a long one. The short one is, what's the surface gravity of the cotton candy planet? The longer one is, what are we learning about the formation of planetary systems? Is that now, how well understood is that?
Yeah, that's getting a lot better, that second question. The first question, I don't have off the top of my head. I'm sure that the internet would probably give you a better and faster answer than I would. I just don't ask the generative AI programs because they'll give you another picture and a wrong answer probably. The understanding how the early part of solar system history evolves, we have a little bit of that from from astronomy, looking out at these early systems. We also have had a big advance in the last couple decades with computers. They've gotten to the point now where we can simulate enough objects that we can look at the early solar system in a granular way. And it is surprisingly different from what we thought, even as early as the 90s now. Things like giant planets migrate, they move around in solar systems. They likely moved around in our solar system. And we find a lot of bodies that we call hot Jupiters that have moved all the way in or now are right next to their parent star. We didn't expect that at all in the 90s. And in the early 2000s, those are the planets that we found a lot of. So this is an area that's just been revolutionized both by what we see out in the cosmos and by what we're able to simulate that we weren't able to before.
So all the exoplanets we have discovered are, I assume, galactic inside our Milky Way. If there's any way we can look at extragalactic exoplanets.
There have been a few, if memory serves, that have been discovered outside the galaxy, but I believe those are other methods. There may be people in the room who know more about this than me, but I want to say that gravitational microlensing, we might have found a few. But that I am not an expert on. I'm mostly a simple country planetary scientist for our own solar system.
Thank you. Thank you. Very exciting talk and very inspiring. About origin of life and how to define if the planet is habitable. Would it be possible to consider any other kind of series of what does it mean life and habitation? Because so far you're talking about pretty much considering kind of like a repetition of what we have here, right, on the Earth. Water-based, oxygen-based, carbon-based. How about any other scenarios of fashion origin?
Oh yeah, that's a fundamental question of astrobiology. You know, is the one example of life that we have representative of all life that exists out there? What we do know is that nothing seems to be quite as versatile as carbon. We have taken a look at things like silicon-based life, but that's very difficult to do. Silicon is quite similar to carbon, but it's not as versatile. So until we can find or, you know, come up with something that's a better example, we're kind of stuck with the carbon-based, you know, example to start with. So that's sort of where we are. We don't know what we don't know is kind of the answer to that question. And I've got one down here real quick.
Yeah, thank you. Yeah, one thing you didn't mention is the possibility of free oxygen in the atmosphere as an indicator of life. How much progress is there now on detecting free oxygen?
So that takes us into the much debated realm of biosignatures. And the question of what is a biosignature and what's not a biosignature. The challenge with those, so the question was about free oxygen in particular, but the problem is we have to find something that shows up in a place where it's unexpected. There are actually environments where you'd expect to have free oxygen in the atmosphere, even without biology. And we see the same thing when we look at other compounds as well. So a lot of the research that I do is on methane on Mars, and we're excited about methane on Mars because it shouldn't be there. And on the Earth, methane is something that's generated by biology. So the methane on Mars, does that come from biology too? But if you go to a place like Titan, for instance, methane is 5% of the whole atmosphere. And so far as I know, nobody thinks that that suggests biology. So it's about finding combinations of gases where we don't expect. Some people out in the astrobiology community have even given up on the gases entirely, and they want to find things like the red edge of vegetation. They feel that's more diagnostic. So yeah, what actually constitutes a biosignature is a hard question. And sort of the classic astrobiology question is trying to come up with a definition of life that doesn't include things like fire, for instance, which does, you know, eat and use energy and reproduce and all sorts of things that we normally think of as being living.
So, Chair, we're okay for two more?
Maybe a bit more off on the fantastical of observing these faraway stars and looking at structures. Can you comment on people thinking they've seen megastructures using these methods?
Oh yeah. So there was a star I remember with a very strange signature that some people were thinking, you know, oh, it's a Dyson sphere that was being in the process of being built or that's falling apart. Typically, when we've seen that stuff, there's been more prosaic explanations. It's one of these things where if you see something, you know, extraordinary, you need to have extraordinary levels of proof. And so we haven't really seen anything like that yet. I know that some people have tried to do things like infrared surveys looking for, you know, the heat signature of these things. And to my knowledge, none of them have been found yet. But it would be so exciting if we actually did find one, wouldn't it?
Last question.
I was just curious if you could comment on the Canadian Space Agency's current priorities and future hopes and plans in this exciting work.
Ah. An easy question to finish. So I should probably say that, my position at the agency is as an advisor. So I, respond to questions they have about the scientific community. I know that the agency wants to see the scientific community grow and to flourish, and to do that in a way that, respects the will of Canadians more generally, as expressed through Parliament. So whenever possible, it's about getting the most science value out of what we can do. Sometimes, the straight line between that and specific missions is hard to make out. And there's definitely a lot of stuff going on. Am I doing a good job as a bureaucrat walking around that question? So unfortunately, I think it's a question of, for us, we're trying to make the best decisions that we can, or the people I advise are trying to make the best decisions they can. But something that, the Canadian community does really well is figuring out with items like the long-term plan what's important to the scientific community, of communicating that to the CSA, but also to Parliament. And, the more organized that we can be as a community, the, better we can have and be part of that conversation about what science we ought to be doing next.
Let's thank our speaker, Dr. Mords, once again.